organicing our way through the class here. We're in chapter 12, I think. Last time we talked about a bunch of different organic compounds, some of which I don't remember, but I think we talked about alcohols, which have the functional group of OH. We also talked about thiols, I think, which have the functional group of SH. We talked about ethers that have the functional group of carbon, oxygen, carbon. We also talked about aldehydes. A good talk about aldehydes. There he is. We talked about aldehydes, which have the functional group of carbon, oxygen, double bond with a hydrogen. And then we had ketones, I think, which has basically 3 carbon run with a double bond there in the middle. So a reminder that for alcohols, as we've talked about, it ends in OL, the name. For thiols, you do not need to know naming, but you do need to know the reaction that we talked about, which is the 2 thiols coming together to form the disulfide bridge. Ethers, you don't need to do the IUPAC name. We're going to do common naming with ethers, which is basically group and ether at the end of it. So kind of go to the oxygen in the middle, look to the left there, look to the right, find the groups, put them in alphabetical order, and then just put ether at the end of it. Aldehydes end in AL, and ketones end in basically ONE. So in terms of naming alcohols, as we talked about, obviously about 3 or more carbons, you do need to give location of where the OH group is located. Ether, since we're doing common naming, obviously you don't have to worry about any of that. Aldehydes, you do not need to worry about where this group is, because as we talked about, it always has to be at the end of the molecule. So either one end or the other. So in the naming part of it, you don't need to include a number for it, but it is number 1 in terms of numbering for everybody else. So wherever that is located, it should definitely be carbon number 1. And for more carbons there with our ketones, you do need to give the location of where the carbon double bonded oxygen is located. Remember, unlike aldehydes, the ketone there will never be at the end, the double bonded carbon, which, by the way, as we also talked about, that is what is known as the carbonyl carbon, right? And that is the carbon oxygen double bond. So that guy will never be at the end in a ketone because it does need 3 carbons in a row, which means the best you could do is, I hope that's just water. You can put it into the second spot there when you do it. Obviously, the functional groups always sort of take the priority. So whichever way you determine to number them, obviously we're going for the lowest number when we do that. Whichever way gives you the lowest number, everybody else that may be attached would be named accordingly. When we have sort of a cyclic structure of, say, an aldehyde or a ketone, once again, you don't need to give the number of where that group is, but it again is carbon number 1 in terms of the ring for anybody else that is attached there. We also talked about making these guys, again, from a primary alcohol. You can oxidize it, and it will again lose those 2 hydrogens there, and that will make your aldehyde. And as we also talked about, you could oxidize this guy one more time. And in this case, we're actually going to insert an oxygen there through that process, and you will make your carboxylic acid, which is this guy here. A secondary alcohol will get you when you oxidize it, again, it will get you that ketone as how we form it. Again, removing the 2 hydrogens there. And as we talked about, no oxidation past that point there. So, that's sort of how we develop these guys. And a step back from these guys, right, is we basically develop our alcohols through the hydration reaction of an alkene, right? So our double bonded guys, right, plus some water, right, will give us our alcohols that we start with here. So again, a primary alcohol oxidized to an aldehyde, oxidizes to a carboxylic acid. A secondary alcohol oxidizes to a ketone. And as we talked about as well, again, a tertiary alcohol will not obviously oxidize as well. Any questions on that stuff there? Okay. So aldehydes and ketones in water, they can form hydrogen bonds with water molecules. After carbonyl carbon and oxygen, a reminder that carbonyl carbon is a polar group where the oxygen is more negative and the carbon part is more positive. So it does make aldehydes and ketones soluble in water, because when water comes by, it is also polar, where it's negative on the oxygen, positive on the hydrogen. So although they cannot hydrogen bond with themselves, they can participate in hydrogen bonding with something like water through the hydrogen on the water and the oxygen on that carbonyl group. And again, that makes it fairly soluble with water. Like most organic compounds, though, as you build up more and more of the carbons, the solubility again starts to drop a lot. So on most things, upwards of about 5-ish or so carbons, and they have the ability to do some type of hydrogen bonding with water, they will be fairly soluble. But, right about in that 5-6-ish carbons on most organic compounds, you really do start to see that solubility drop, even though they may have a group that can hydrogen bond with water. And that's again because, as we talked about, they get really too large of a nonpolar part, and it really gets in the way of sort of water being able to get in there and sort of interact well with it. So as you see here, sort of the same idea. This is our aldehydes are fairly soluble, and some of our ketones as well. But again, as you start hitting that 5 to 6-ish mark in terms of carbons, you do start to see the solubility really start to decrease. Remember that really things are soluble in each other when they're able to interact the same way that they can interact with themselves. So water obviously interacts with itself through hydrogen bonding. So anything that has the ability to sort of hydrogen bond with water will typically make it soluble in that case. And again, as long as you don't have too big of a nonpolar part. We talked about some of these ketones and aldehydes. Again, formaldehyde, which is methanol, which is basically our 1-carbon aldehyde here, obviously used to preserve things in biology. And we talked a little bit earlier about propanone, which is basically also common name as acetone, used as a solvent, nail polish remover. Also, some aldehydes and ketones give us some flavors and stuff that we see. An aldehyde for almonds here. And I think there was sort of a question earlier about how the aldehyde group kind of goes onto a ring the other day. And again, just to remind you, this is sort of how they will be. The aldehyde group, again, cannot be part of or integrated into the ring because of that hydrogen that's there. So you'll kind of see it, sort of as a group that's off the end of it. And that's what we see here with both of these. So that's sort of the aldehyde group that's coming off of it. This would basically be named benzyl aldehyde because that's a benzene ring, and that's an aldehyde group there. So benzyl aldehyde is the name of it. This is our ketone here for cinnamon. We got a 3-carbon run here. And again, our double bond there in the middle of the 3-carbon run, giving us our ketone. All right, so let's go through these here and classify them. Thank you. As ketones or aldehydes, let's start with the first one. First one, aldehyde or ketone. First one is a ketone. Here is the 3-carbon run that you need, along with the carbon oxygen double bond in the middle there, and that is a ketone. Again, to remind you on the naming part of it, that is 1, 2, 3, 4 carbons, which means this is butanone. And this would be basically 2 butanone, but you don't really necessarily maybe need the 2 here, but most people will still put the 2 in that particular case. Coming to B, we got a aldehyde. So that is the group right there. So that's an aldehyde. And the name of this one would be 1 carbon, 2 carbons. So that's based off of ethane. So that will be ethanal, Al at the end of it. Coming to our C, we again see the same group, which as we talked about is going to be at the end there. So that is going to be a aldehyde. In terms of naming, we got 1 carbon, 2 carbons, 3 carbons, 4 carbons. You can actually get it multiple ways, but 4 carbons is the most there. 4 is based off of butane, so that would be butanal in this case. Again, you do not need to give the location of where that double bond is located, but it will be carbon number 1. So that's carbon 1, that's carbon 2, and that's carbon 3. And at carbon 3, we have a couple of methyl groups hanging out. So that is a little 3,3 dimethyl. I wrote it way over there. Butanal. I was hoping to join up there. Any question on that one there? Lastly, here, our last guy is a aldehyde or ketone. Our last guy is a ketone. This is carbon, carbon, carbon. So that's your 3 carbons in a row. And off that center carbon, right, is our double bond, which makes it a ketone. This is a cyclohexane ring. And again, it's actually a ketone, so it becomes cyclohexanone. O-N-E. I think I ended last time with that one. I think I drew it last time. Any question on any of those there? Okay. All right, so why don't you name a couple of these here as well, and then let's draw a couple more here just to make sure. Why don't we draw two bromo, 4 ethyl, all right, so 4 ethyl. Let's go with octanol. Why not? All right, so draw that guy and then name the other 2. Okay, let's take a look and see. So first off here with A, you hopefully can recognize this group right here is a ketone. So obviously we're dealing with ketones, even if they weren't nice enough to tell us these are ketones. We have, in terms of longest carbon change, I think it's just straight across on this one. So it's 1, 2, 3, 4, 5, and 6. Bless you. That's going to be hexanone. And in this case, we do need to give the location of that carbon oxygen double bond. And you can just probably see that if you go right to left, that's going to give you obviously the smaller number. So that's a little 2-hexanone action happening there. Yes. Any questions on that one there? Coming to the one on the bottom, once again, if it didn't tell you, you should be able to recognize this part of it here as a ketone. And we would count our carbons, and it is 1, 2, 3, and only 4, as that is not a carbon, that is a chlorine, right? So that is 4 carbons, which is based off of butane. This would then become butanone, and we'll go with 2 butanone going this way. And then that would be 4 chloral. I'll try to squeeze it in there, 2 butanone. Any questions on those two? All right, drawing the guy at the top, we work backwards here. So octanal, that is a lot of carbons. All right, so 1, 2, 3, 4, 5, 6, 7, and 8 for octane. Al means that it is a aldehyde group there at the end. And again, you could put it on either end. I'm going to put it, I think, over here at this end. So because I did put it over there at that end, that would make for me this guy right here, carbon number 1. Obviously, if you put it on the other end, it would be carbon number 1 on the other end for you if you chose to do that. So for me, going down 4, 1, 2, 3, 4, we would have an ethyl group, which is a 2-carbon group. And going to number 2, there is a bromine. And really everybody else here is just going to be hydrogen. So guy at the far left here needs 3. Guy next to him needs 2. Also 2 next to him and 2 next to him. Guy here where the ethyl group is just needs 1. Guy next to that guy needs 2. Guy with the bromine needs 1. And that is it all the way through there. Any questions on that one there? Or any of those? Yeah. Yeah, so if you're asking if you put the group over here on the left, this would be carbon number 1, and then you would just go down this way to where 4 is, and you put the ethyl group, and then to 2, you'd put the bromine. Yeah. You would in this case as well. The only way the number 1 carbon would be on the left is if you put the group over there on the left. Yeah, so never, if your question is, would this guy be carbon number 1 ever? It wouldn't. No, it's not the way I drew it. Because this is the functional group. So this guy has to be carbon number 1. But if you did happen to draw it the other way and put the functional group on the left-hand side, then that would move the carbon number 1 over there, but it's still that functional group that's the carbon number 1. Yeah. Yep. Other questions? Okay. All right, so we've kind of dealt into some of these reactions here, so we won't probably spend a bunch of time on these, but we'll just go over them again just to make sure officially. Obviously, reactions with I put them all together there. I think alcohols, thiols, aldehydes, and ketones. They can also obviously do this reaction here, which is a combustion reaction that we saw earlier: CO2 and water and O2. A little flaming dessert sounds good. One reaction that we didn't talk about here is the dehydration of an alcohol. So remember, a hydration of an alkene will give us an alcohol. So when we put the water onto the double bond, we get the alcohol. But if you provide a acid as a catalyst, and that's what the H plus here is, a catalyst, it's not really doing much other than sort of speeding up the reaction. And heat, which is also sometimes signaled by a triangle on top of the arrow. What you're going to basically do is drive off the water and the alcohol. So basically the water is going to come off the exact same way that the water goes on, or the water goes on to the alkene. So to review, the water, when we have an alkene, basically we could think of it as HOH as water. We do make our double bond into a single bond. And remember that in this particular case, one of the carbons will get the hydrogen, so I'll make a different color. We'll just redraw these guys, H, OH. So one will get the OH, and one will get basically the hydrogen. So when we sort of dehydrate the alcohol through heat, we basically take it off the same way. So what we do is we go and if we were to heat this up, not delta H, sorry, just delta there. what's going to happen is we're going to basically take off water. And the important part here is it's always going to obviously be the OH. And once you find that OH, pretty much you go to the carbon next to it and you take off a hydrogen. It really doesn't matter which one you take off, but you got to pull off a hydrogen. And that's where the water is going to come from. The hydrogen and the OH never comes off the same carbon. So just like they go onto two different carbons, they come off the two different carbons as well. And the result of that is obviously we would get water that would be formed. And once again, nothing really changes in that molecule other than you just take those two things off. So you can redraw it exactly the way it looks without the water part. And now if you just look at the carbon, it's short a bond because we took those two things out, and we will put back our double bond. So the dehydration of a alcohol gets you back to an alkene. So it's basically the reverse reaction of making an alcohol. When you make an alcohol, you take the alkene and then you get the alcohol. And when you heat up an alcohol and dehydrate it, you start with the alcohol and you get back the alkene. Now, in this situation where we dehydrated this alcohol, there really wasn't a choice in terms of what carbon to take the hydrogen off of. So if you remember when we added the water here to the alkene, these were referred to as unsymmetrical addition. And if you are adding H and something else like OH, and the carbon and the double bond when you started with had different numbers of hydrogens, right? The hydrogen would end up at the one that had the most hydrogens. So when we actually get into a situation where there is different numbers of hydrogens on the alcohol, we would actually take the hydrogen off of the one with the least number of hydrogens. So we kind of do the opposite when you take it off. So for example, here, we'll take a look here, draw here. Let's see here. If we had something like yeah, that's not a good example. Let me take off a hydrogen here. Let me do. Let's do this. We'll do this one more carbon, I think. Okay, so here we would dehydrate this guy. So we're going to heat it up basically. So in this case, we would take the eraser. We would take that guy. We're definitely going to take the OH, right? And now we are going to look to an adjacent carbon. And our two options is to either take a hydrogen off of this carbon or a hydrogen off of this particular carbon. And again, when we would put the hydrogen on, it would normally go to the one that had the most to begin with. So here, when we take it off, we're actually going to take it off the one that has the least number of hydrogens. So in that case, it would be the carbon here that we would want to take off. That means that the double bond would actually be laid between those two carbons. Yeah, so we would put the double bond back in that spot. So once again, here we would go with our water that would come off, and I'll draw it up on top. But again, nothing here is going to change other than we're just going to take the water out. So we'll have our carbon, our 3 hydrogens on the left there. We'll have our carbon with a hydrogen. This is where we took out the OH and the H. So we're going to make a double bond right there. And now we're just going to continue on. There's still a hydrogen on the bottom. There is a carbon over here. And now we would have, again, our alkene. So if it happens to be you're taking the OH off and there's a couple of carbons to sort of choose from on either side, you would remove the hydrogen with the least number of hydrogens. Again, sort of opposite of how we put it on, which goes to the most number of hydrogens. Any questions on that there? Okay, so that's just a little wrinkle there with a dehydration. Obviously, we talked about oxidation and reduction reactions. And again, really in organic chemistry, we really do focus in on the oxygen and the hydrogen. A reminder that the oxidation, as it says there, basically as you go from reactants to products, somebody gains oxygen or somebody will lose basically H2 as you go from reactants to products. Reduction is pretty much the opposite definitions as it says there. Reactants to products, somebody loses oxygen. And from reactants to products, somebody gains H2. So we saw sort of this definition of oxidation when we were talked about earlier, obviously these reactions. We saw the definition of gaining, of losing H2 as we went through those oxidation reactions. And as we went to our carboxylic acid, there was the other definition of gaining oxygen. So those are really the two sort of ones that we look at. So as we talked about the oxidation of a primary alcohol, once again, it is always, as we've talked about, the hydrogen of the OH and a hydrogen off of the carbon that's attached to it. Once again, when that comes off, that basically gives us H2. And we do need to kind of close that gap by making that into a double bond, basically. Otherwise, we're going to be short bonds. And as we just talked about earlier there, that obviously gives us our aldehyde. Now, that is the oxidation reaction. The reverse of that reaction is the reduction reaction. And that is when you actually would add just H2 to your aldehyde. So if you did that going the opposite way, starting with the aldehyde, and once again, it doesn't matter how many carbons is on this aldehyde, but if you added H2, it is going to add pretty much always to the functional group. So it's going to add right in here to this guy. Now, when we look at this guy, obviously the carbon doesn't have room for any addition, and really neither does the oxygen, since we don't really put them a lot of times. There are non-bonding electrons actually on those oxygen. So it's kind of full at this point. It doesn't really have room, even though a lot of times in organic chemistry, you sort of omit the dots. This oxygen actually has the lone pairs that are sitting there as well. So to make room for it, what happens is very similar to what we see with a double bond that we add hydrogen to. When we add hydrogen to a carbon-carbon double bond to make room for the hydrogens coming in, we have to turn it into a single bond. And that's exactly what happens when we add hydrogen to an aldehyde. This double bond becomes a single bond. So once again, you could literally draw it exactly the way it is. And if you did, you would have your hydrogen, your carbon, your hydrogen. You would have your carbon now turning this into a single bond and putting an H at the end. And now what goes in is frankly a hydrogen to the oxygen. So I'll make this guy blue. Hydrogen to the oxygen and a hydrogen over here to the carbon. And we get our alcohol back. So it's the reverse reaction. So oxidation reductions are basically reverses of each other. So in this case, the oxidation part, we're taking off the hydrogen to make the aldehyde. But if we wanted to get our alcohol back, we would just simply put the hydrogen back on in the same location and we would get our alcohol back. Any questions on that there? Here's our primary guy. As we also talked about, it can further oxidize the aldehyde to a carboxylic acid. And in this case, it is the definition of adding oxygen. So the oxidation of the aldehyde to the carboxylic acid everything is identical here, except that you just insert the oxygen basically by the hydrogen, and that's always where it will go. So once again, if you had to redraw that, you just copy what's there. And on most of these products that you need to draw, you pretty much have 90 some odd % of the molecule drawn for you by frankly just copying what was there before you. You just got to change one part of it and you should have the correct thing. So you really shouldn't overlook what's drawn on this side, because it pretty much is the same thing that ends up on this side with a very small modification to it. So some people just look and go, I'm not really sure what we're going to make. So for the most part, you pretty much could use what you start with and just change that small part, and you'll have, like I said, almost 95 to 98% of it kind of there for you already on the picture. This is our secondary alcohol, which again, the same thing's going to happen. We're going to take a hydrogen off of our OH group, going to take the hydrogen off of our carbon that's attached there. We're going to insert our double bond there in the oxidation step. Once again, we would get our H2. Obviously, heading in the opposite direction, that would be the reduction reaction, which sometimes in books and stuff, they'll just write like maybe like H2 or something like that, you know, to tell you it's the reduction part that's happening. But works the same way as the one we just looked at. So again, if you had your alcohol there, your secondary alcohol, actually your ketone, I guess, would be the better one since we're starting with that. So if we had our ketone here and we wanted to do our reduction reaction, which means we're adding hydrogen. Once again, it is this part that is the important part. And just like we talked about before, we need to make room for the hydrogen. So just going to single bond it up. Everything stays exactly the same, except that I'm now going to turn this into a single bond, and everybody else remains the same. So frankly, as you can see, you can pretty much redraw the product in the second by copying what's there. I highly recommend you do that because you're halfway, more than halfway to the end. And at this point, we just need to put a hydrogen on both spots. So I'll make it a different color. We will put a hydrogen up there to get our alcohol back. And to finish out our carbon, we would put a hydrogen there. And those are the hydrogens, obviously, from the H2 in this case. Any questions on that? So the reverse of an oxidation of a ketone, which is a reduction reaction, you basically get back your alcohol. So again, they're opposites of each other. Any questions on that? As you can see, pretty much all the action right there is pretty much where all the action happens, and that is pretty much the case. I think I've mentioned it before as we've been doing some of these, that, you know, there's no real funky stuff that happens, like it automatically makes a happy face ring or something like that, you know, or gains 40 different carbons or anything like that. So no funny stuff. We also talked about, I think as well, that a tertiary alcohol will not go through oxidation. And really the reason it will not go through oxidation is it is missing a crucial sort of hydrogen. We don't really go through the pathway as to how these reactions take place, but part of the pathway and necessary for it to actually occur is it needs to have that extra hydrogen there on that carbon. Because it's lacking it, you will get no oxidation products. And obviously you can't go backwards because you don't get anything. It just basically stays the same. Any question on those guys there? All right. So methanol, also known as methyl alcohol, highly toxic, found in windshield wiper fluid. All right. Sounds like fun. Ethanol is the alcohol of alcohols. Yes, there you go. We talked about this reaction as well, but again, a reminder, this is what you do need to know for thiols, in addition to obviously the functional group of a thiol. And this is really the formation of what's sometimes referred to as a disulfide bridge or disulfide bond. And remember that the thiol groups is this guy containing. So basically what happens here is we basically just take out the hydrogen. The H2 comes out, a hydrogen from each, and you basically just squeeze everybody together. So you take, as you see here, You know, you could have something like this, which is a thiol, and you could have another thiol with less carbons. It doesn't matter. So when you put two thiols together, this is going to be an oxidation reaction, because I am taking out H2, right, which is a definition of oxidation. Now, at this point, frankly, all you need to do is start writing here and end here, take out what's in the box, basically. So you're just going to put all that together, CH3, CH2, S2S, and a CH3. And there's our disulfide bond that basically formed. So the oxidation of a thiol will result in this disulfide bond, and it essentially is just taking out the hydrogen. By the way, if I wanted to break that back apart, I would then put the hydrogen back in, yeah, and that would be the reduction reaction, which would go in the opposite direction. And you may wonder, where do I know to break it? It should always break right there, yeah. So basically you break it where you put it together, and when you break it apart, guy on the left gets a hydrogen, guy on the right gets a hydrogen to make the SH group. And that is basically the opposite reaction, which is a reduction reaction, because in that case, we're adding the H2 going in that direction. Oxidation going in the other direction, we are removing the H2 to put it together. Any questions on that there? All right. Now let's talk about a couple of tests that help us distinguish aldehydes, you know, from ketones. Because the aldehyde, as we just saw, again, can kind of go that extra step, if you will, and our aldehyde, like we see here, can be oxidized to our carboxylic acid. We're able to use a test like the Tollens test to help us distinguish between, say, a ketone, which really will not oxidize. So you won't get any reaction that will go beyond that. So when we do this, what happens is, if you remember, there are redox reactions, which means if somebody gets oxidized, somebody else gets reduced. And what happens in this particular case is the ethanol gets oxidized by putting an oxygen there. So this guy gets oxidized. And it is actually the silver with a +1 charge gets reduced. And the only way the silver can get reduced is if the ethanol gets oxidized. So the ethanol has to get oxidized, or the aldehyde has to get oxidized here in order for the silver to get reduced. What it ends up doing is it creates what is sometimes referred to as the mirror test, because it creates this silver color and it looks like a mirror, and that would be a positive result that what you started with was an aldehyde that was oxidized to a carboxylic acid. The Tollens test sort of recognizes that reaction. You will get nothing occurring in this case. You won't see the silver develop in the case of a ketone. So again, that's how you know sort of the difference between if it was perhaps an aldehyde or a ketone that you started with. If this thing really did take place, or you know that this was a positive test, how do we draw the product of that? It is, again, fairly straightforward. All you have to remember is, if my aldehyde does get oxidized, the only thing that changes is I'm just going to throw an O right there, basically. So you basically just draw it exactly the way it is, and you pop your O in there, and that gives you your carboxylic acid. And that is always the case, whether it has 2 carbons or 400 carbons and a bunch of other stuff attached. The only thing that changes as you oxidize an aldehyde is you put the O in front of the H to make a carboxylic acid group, and it's always that. Everything else stays exactly the same. By the way, this is ethanol, right? This is a 2-carbon carboxylic acid group, which is known as ethanoic acid. Carboxylic acids are named with oic acid at the end. So instead of ethanol, you kind of drop the phos part and make it oic acid, so it becomes ethanoic acid, also known as acetic acid as well. And that's basically vinegar, what you were looking at there. So tolerance test is one test is sometimes used to distinguish between a ketone and an aldehyde, or I guess a better way to say that is to know that you had an aldehyde would probably be the better way to say that. The other test is, I think what you guys did, which is the Benedict's test. The Benedict's test basically works the same way. It's able to distinguish between aldehydes and, that they were there. The difference is the color that changes. In this case, we're actually using copper. And we're using copper 2, and copper 2 in its aqueous form is a bluish color. And if it gets reduced, it will go from copper 2 to basically copper 1. And copper 1 is kind of a red-orange type color. And if your solution goes for a red-orange color, then it is positive for an aldehyde. Once again, the only thing that would have been able to cause that occurrence is an aldehyde that got oxidized to a carboxylic acid. So again, this is a way you can tell if it was an aldehyde that was there before. Any questions on that one there? And here's the coloring here. Again, kind of a negative test, positive test on the right there. Again, reduction of these guys is what we were just talking about. You could get your alcohol back. Kind of jumped the gun there. And obviously you could get your alcohols back from reducing our aldehyde or ketones by taking the double bond on the oxygen off and putting our hydrogens on. All right, so why don't you take a moment here and figure out what is the product of this oxidation here? Primary, secondary, tertiary, secondary. Which, by the way, when I oxidize a secondary alcohol, what should I end up with? Not the aldehyde, but a ketone, yeah? So it's good to know where you would end up. Also good in a multiple choice question because how many ketones are on the answer sheet? Just one, yes, and I would be done without drawing a thing, yes. So it's good to know, what you are making. It's also good to know where you end up, but let's draw it anyways, just to verify that we did choose the right one. But it's never a good idea to, think about these things to kind of help you out maybe on some questions here. So because this is an alcohol, we're going to get rid of hydrogen on the oxygen always, and the hydrogen on the carbon. Everything else will remain exactly the same. So I'm just going to copy it exactly the same. And once again, here I should then include a double bond where I took off the hydrogen, and looky, it matches. So that's good. Yeah. So again, sometimes good to know where you're going, right? That's why directions are good sometimes, right? Rather get in the car and go, I know where I'm going. That's all right. We'll get there eventually. There's only so many streets to go down. All right, select the product when we take this alcohol, undergoes both of those. I think our letters are in the wrong spots. We'll go C there and B there. How's that? There you go. All right, so we're going to take this alcohol. We're going to oxidize it twice. We're looking for both products, I think. Okay, so let's take a look and see. So once again here, I mentioned it's an alcohol. What type of alcohol are we starting with here? Primary, secondary, tertiary? Primary. So by the way, when I oxidize a primary alcohol, I get starts with an A. I do get an aldehyde, that's good. And if I oxidize the aldehyde, I get starts with a C, carboxylic acid. Yeah. So once again, if you know those things, you don't even need to draw anything because the only aldehyde on the choice here is number 3. Yes. Which means I could just bubble 3 and be done. By the way, the only carboxylic acid on the list is number 4, which means I could bubble in 4 there and be done with this question very, very quickly. But let's say we didn't do that and we want to draw it. So we will do our oxidation here of our first one. And I'm just gonna kind of draw out the hydrogens on the last one there so we can see everybody. So we're going to oxidize this alcohol, which means we will take the hydrogen off of the O and one off of the C there. And then that should get us our aldehyde that we do expect to occur, where we would then turn this guy into a double bond and keep the hydrogen, which should match that. Once again, we would then go through one more oxidation. And on the second oxidation here, all we have to remember is I'm going to insert an oxygen right there. And that will give me my carboxylic acid group. And that should match the guy right there. Yeah. So very important to sort of know, what's going on, what you should expect. It also makes drawing a little bit easier because you should obviously know what the functional groups look like. So it helps you sort of do the drawing part of it as well. Any question on any of those there? Yeah. It would be, yes. Let's get to it. Other questions? All right. All right, so let's try this one. We're going to do 2-propanol. Undergoes an oxidation and it undergoes a dehydration. So draw both of those things. And I guess 2-propanol as well. All right. To start with, you got to draw this guy. So we're going to go backwards there. So propane is 3 carbons. So we'll do 3 carbons. We have an OL, which means it's an alcohol, and we have a 2, which means the OH group is hanging out there, carbon number 2. We'll put our hydrogens in here to finish it out, and I'm going to actually just draw my hydrogen there, just to draw it out. So that is what type of alcohol? This is a secondary alcohol, which means when I oxidize that secondary alcohol, I should end up with a ketone, right? So now I know what I'm looking for here. So we know that this type of oxidation of an alcohol involves the hydrogen on the O, the hydrogen on the carbon that's attached to the O, and we're taking those guys out. So that gives us the H2 that comes off. Once again, we're not going to do anything fancy other than copy what's already there. So CH3, our C, our O, and CH3. And to complete our ketone, this O now needs to be double bonded up. And now we have our ketone that has been drawn. Yeah. Any questions on that one? So that would be AA, obviously, here. B is we're going to do the dehydration of the alcohol. So we'll start with our secondary alcohol again. So I'm just going to redraw it. In this case, I'm going to actually draw all the hydrogens just so we can see them. So once again, this is our 2-propanol. And when we do a dehydration, we're going to heat it up. A little delta symbol. So dehydration means we're going to remove water, right? So clearly the water came on as H and OH. So I know the starting point of where I should focus in on is definitely the OH. Now I need to remove a hydrogen once again, not from the same carbon. So from a carbon next door. In this case, I got 3 hydrogens on the carbon to the left, 3 hydrogens to the carbon on the right. Doesn't matter in this case. It does not. They're both the same. So you can take it off of either carbon in this case because they have the same number of hydrogens, right? So it's only when they don't have the same number of hydrogens that you have to sort of worry about it. And in this case, I'm just going to simply take a hydrogen off of there. Now, between where I took the OH and the hydrogen, that is where we're going to put our double bond in, right? So everything else will remain the same. We have an alcohol that has been dehydrated to an alkene is what we should expect to happen here. And once again, everything will be the same. except that obviously I'm going to remove my OH and my H, and I'm going to put a double bond where they remove those guys, and we're going to keep the other hydrogens. Then we have our alkene. Any questions on that one? Now, if you remove the hydrogen from the guy to the left, which would have been perfectly okay in this case, you would have just double bonded to the guy to the left. Yeah. The reason it doesn't matter is because let's just say we decided to take a hydrogen off of this carbon, just to show you. If we took the hydrogen off of the carbon on the left, we would end up with this. What is the name of this guy? If you had to go name this guy. There's how many carbons? 3. What type of a molecule is it? It is a alkene, which means 3 carbons is propane. With a double bond, it is propene. Do I need to give location to the double bond? Actually, in this case, you don't really need to, because if you put it on the other end, it's going to be the same, right? How about this guy? This guy is also an alkene. It has how many carbons? Right. And if you were to name that guy, you would end up with propene. It's the same thing in this case. And you end up with the same thing regardless of where you did the hydrogen in this case, is because they both had the same number of hydrogen to begin with. So it doesn't really matter, which one you took it off in this case because of that. Any questions on that there? Okay. One with organic chemistry. I like it. All right. Write the structure and name the product that you would get, yeah. If you mix the tolerance reagent with each of these guys. Well, that's the common name, so we'll do a different one. Let's do a different one altogether. Let's do the butanol. Let's do propanol. That. And ethyl methyl ketone is the common name, so we'll do our official name there. Let's take a look. We'll start with drawing what we got here. So butanol, Al tells us it is a aldehyde, and it should have 4 carbons. Once again, I'm going to put my group here, and since there's nothing else attached, we're just going to put in our hydrogens at this point. Propanol, also a aldehyde. Propane is 3 carbons. Again, I'll put my group over here, and I drew the ketone on the bottom. So first off, we just think about what we want to do here and what's going to happen. I'm going to have an aldehyde that I'm going to oxidize. So that is this guy here. When I oxidize an aldehyde, I should end up with a carboxylic acid, yeah? And the functional group of a carboxylic acid is this group. Once again, the only difference between those 2 functional groups is the oxygen, yes? Oxygen there, no oxygen there, yeah? So that is, again, the only thing that should change on our aldehyde is we're going to, again, just insert the oxygen in front of the hydrogen. So we can redraw our guys here, going through the oxidation by, frankly, just copying it exactly the way it is. And then we just need to remember that I'm going to insert my oxygen in front of my hydrogen. Same thing here. If we went this way, we're going to copy it exactly the exact same way. And once again, I'm just going to insert my oxygen in front of my hydrogen. By the way, this is a ketone, this guy, right? If I oxidize a ketone, what do I get? Get nothing. Yeah, so no product's going to be made out of that. So this one is called butanol. Carboxylic acids end in oic acid. So this guy over here, which would have 4 carbons, would be known as butanoic acid. Oic acid, yeah. Which means this guy down here, which has 3 carbons based off of propanol, would then become propanoic acid. Yeah. There's the name, yes. Much like the aldehyde, because of this H at the end of this functional group, it will always be at the end. Yeah, so just like the aldehyde, that carboxylic acid will always be at the end. Also, like the aldehyde, because it always has to be at the end, you do not need to give the number of where this is at. But for numbering other things that might be there, that would definitely be carbon number 1. Yeah. So for example, if we threw something onto the end of this one here, you know, like this would be 1, 2, 3 propanoic acid. This would be carbon number 1. Carbon number 2 would be my chlorine. This would be 2-chloral propanoic acid. So again, much like the aldehyde, the carbon oxygen double bond always going to be carbon number 1, but you don't need to incorporate it into the carboxylic acid name, but you do use this carbon number 1 to number anything else that may be there in terms of the numbering. Any questions on that there? All right, we're laid up there for today. Let's talk about a couple